Section 13.9 is on applications of extrema of functions of two variables. In the previous section, we used the second partials test to determine if there are relative maxima or relative minima of a function of two variables. So in this section, we're going to solve some optimization problems involving some functions of several variables. In this example, we want to find the maximum volume of a rectangular box. This rectangular box is resting on the xy plane with one vertex at the origin, and the opposite vertex lies on the plane 6x plus 4y plus 3z equals 24 as shown. Find the maximum volume of such a box. So what we want to do here is find the equation that we're trying to optimize. The equation that we're trying to optimize, or the function, is the volume. The volume of a rectangular box is going to be the length times the width times the height. And the height of this box is going to be determined by the equation of this plane. So if we have x for our length, y for our width, and z for the height, we want to maximize that volume function. Okay, so again, since one of the one vertex of the box lies in the plane, and you take this equation for the plane and solve it for z, you get z is equal to 1/3 of the quantity 24 minus 6x minus 4y. And then you can write the volume of the box as the length times the width times the height. And if we have x, y, and z, the volume is x times y times z, but we're going to replace z with what it equals on the plane. We call that a secondary equation, where our volume is our primary equation. That's what we're trying to optimize. So volume in terms of just two variables is length times width times height. If x is the length and y is the width, then the height is our z. And using that equation for the plane, we can find out what z equals in terms of x and y. So here we have a function of two variables, and we want to find the relative extrema. In other words, we want to find the relative maximum, the maximum volume of the box. So using the second partials test requires us to find a critical value. The critical values are where the partial derivative with respect to x and the partial derivative with respect to y are both equal to 0. So what I would do is I would recommend distributing this x and y and then taking those partial derivatives with respect to x and y. All right, so when you distribute the x and y, we can then take the partial derivative of this with respect to x, treating x as a variable and y as a constant. You get this as your partial derivative with respect to x. You can also take the partial derivative with respect to y, and you get this. Now we want to find out where those are both equal to 0 at the same time. Notice here a y has been factored. That's a common factor. So if we factor out the y over 3, you're left with this. And in the second partial derivative, we factored out the x. Now, if you have two factors that are multiplied together to equal 0, either the first factor equals 0 or the second factor equals 0. Now, if you set y over 3 equal to 0, you get 0. And if you set x over 3 equal to 0, you get 0. That's one of our critical points. The other part, if we set 24 minus 12x minus 4y equals 0 and this factor equal to 0 and solve this system of equations simultaneously, you can use the substitution method, the elimination method, or you can even use the matrix method if you set it up in the form. Refer back to some of the previous sections where I showed you how to use a calculator in the matrix mode to solve a system of linear equations. Now when you do that, when you solve that system algebraically, the critical point is 4/3, 2. So this volume, which is a function of two variables, has two critical points. Now, if the critical points yield an x of 0 and y of 0, then the volume of the box would be the length times width times height would be 0 times 0 times whatever the height is, and that would have a volume of 0. So that certainly does not yield a maximum volume. At the other point, the other critical point, where you can apply the second partials test. Go back to the first partials and continue to take the partial derivatives again with respect to x, y, and then do the mixed partial derivative. The second partial with respect to x is negative 4y. The second partial with respect to y is negative 8x over 3. And then that mixed partial is 1/3 the quantity 24 minus 12x minus 8y. Now we're going to find the value of d taken by multiplying the vxx times vyy minus the mixed squared when you plug in 4/3 for x and 2 for y. So when you plug in 4/3, when you plug in 2 for y here, you get negative 8. If you plug in 4/3 for x here, you get negative 32 over 9. And then when you plug in both the x and the y, you get this value. When you simplify this whole thing, you get the 64 over 3. Now that's our value for d. Again, refer back to the second partials test. If d is positive, if d is greater than 0, we either have a relative maxima or relative minima. If you look at the sign of Vxx, it's a negative 8, so that's less than 0. That means we have a relative maxima of the volume. So we can conclude, again, using that second partials test, that the maximum volume is found when x is 4/3 and y is 2. Now, if we plug that back into our original volume function, we can actually determine what that maximum volume is by evaluating to get 64 over 9 cubic units. Okay, note that the volume is 0 at the boundary points of the triangular domain of V. So again, when we found that critical value of 0, we can exclude that from our answer because that would not yield a maximum volume. But at this critical point, we do have a maximum volume at 64 over 9.